Welcome back to EEE101. Today we will talk about step response of RC circuit. In step response of RC circuits, the circuit containing the capacitor also contains one or more independent sources after the switching. This is the main difference between source-free RC circuit and step response of RC circuits. Let's consider this circuit. In this circuit, we have two switches. Both the switches are operated at the same time at t equal to 0, and we want to find out the capacitor voltage after the switching. The left switch was open for a long time, and at t equal to 0 this has been closed. On the other hand, the right switch was closed for a long time, and at t equal to 0 it has been opened. Let us look at the circuit for t less than 0, that is before switching, and for t greater than 0, that is after the switching. This is the circuit for t less than 0, and you can see that this circuit is the same circuit before the switching for source-free RC circuits. That is, the circuit before the switching is the same for source-free and step response RC circuits. And if we look at the circuit after the switching, this is what we get. This is quite different from source-free RC circuits because in this circuit, even after the switching, we have an independent source Vs. The treatment for t less than 0 circuit is the same in step response and in source-free response. Here, we have seen before that the DC condition exists, and since the DC condition exists, the capacitance behaves as an open circuit. So under open circuit condition, the capacitance voltage is equal to V0 for t less than 0. Using the continuity property of the capacitor voltage, we obtain the initial condition, which says that the capacitance voltage just before the switching is equal to the capacitor voltage just after the switching, and both are equal to the initial value V0. This condition is known as the initial condition, which we have already seen before in source-free circuits. So the initial condition of step response RC circuit and the source-free RC circuit are the same. Now we look at the circuit for t greater than 0. Here the presence of this voltage source Vs makes the two circuits different. We assign a current IC through the capacitor and a current IR through the resistance. Using KCL at the plus node, we write IC plus IR equal to 0. IC is C dVc dt, and IR we can express using Ohm's law. So this is the equation we obtain. Rearranging the terms, this equation can be written in this form. Now we do a variable substitution. Vc minus Vs is called X. X is the substituted variable, and dVc becomes dx. So after the variable substitution, we get this equation dx by x equal to minus 1 by RC dt. If you remember the solution for source-free RC circuit, you will find out that this is the same equation for the capacitor voltage of the source-free RC circuit. So the solution is also the same. X is equal to a e to the power minus t by RC. Here a is the constant of integration. Now x is Vc minus Vx. So Vc is x plus Vs. Using that, we write the capacitance voltage is Vs plus a e to the power minus t by RC. To find the integration constant A, we look at the circuit at t equal to 0 plus. The value of the capacitor voltage at t equal to 0 plus is known from the initial condition, which is equal to V0. From this equation, if we put t equal to 0 here, we get Vs plus A. So this is what we obtain. The integration constant A is now V0 minus Vs. This is the expression of A, V0 minus Vs. Also, we defined tau the same way as we did before for RC circuit. The time constant tau in this case also is equal to RC. With these two relationships, the capacitor voltage is expressed in this way: Vs plus V0 minus Vs e to the power minus t by tau for t greater than 0. This is our desired results mathematically. Now we want to know how this function looks graphically. There are actually two possible ways this function can look like. Let's see one by one. We first considered the situation when the initial value V0 is greater than Vs. So for t less than 0, the capacitor voltage is constant at V0. At t equal to 0, after the switching, the capacitor starts discharging and the capacitor voltage decreases. However, unlike the source-free situation, the capacitance voltage does not discharge all the way to 0. Rather, the capacitor voltage gets fixed at a final value Vs after 5 tau time. So, the difference between source-free response and the step response is here. In source-free response, the capacitor voltage discharges all the way to 0. But in step response, because of the presence of the independent source in the circuit, after the switching, the capacitor does not discharge fully. It discharges partially. When the capacitor voltage becomes equal to Vs, the capacitor voltage gets fixed and it does not discharge anymore. So this Vs voltage can be treated as the final voltage of the capacitor. V0 is the initial voltage and Vs is the final voltage. And how much time do we see that it takes practically for the capacitor voltage to reach the final value? This answer is same as the source-free RC circuit case. It takes practically 5 tau time for the capacitor voltage to reach the final value. So this is first of the two possible graphs for our capacitor voltage. The other graph looks like this, and it happens when the initial value V0 is less than the final value Vs. Here, for t less than 0, the capacitance voltage is constant at V0. That's alright, but after the switching, the capacitor does not discharge. It starts charging, and after 5 tau time, it reaches the final charged voltage, which is equal to Vs. So in both these graphs, V0 is the initial value, Vs is the final value. It takes 5 tau time to reach from the initial value to the final value. But physically, in the two circuits, the capacitor is behaving in two different ways. In the left circuit, the capacitor is discharging after the switching. In the right circuit, the capacitor is getting charged after the switching. And remember, we can divide the different times for both graphs into three separate time zones. The first time zone is t less than 0. We have that time zone here as well as here. The second time zone is when t is between 0 and 5 tau in both graphs. And the third time zone in both graphs is when t is greater than 5 tau. So we want to see how the capacitor behaves in each time zone. Remember, I have already mentioned that the capacitance voltage reaches the final value Vs after 5 tau time. Now, if I want to find the capacitor behavior in each time zone, we can form this table. For t less than 0, the capacitor voltage is constant at V0. If the capacitor voltage is constant, then DC condition prevails and the capacitor can be treated as an open circuit. For t greater than 5 tau, also the situation is similar. The capacitance voltage is equal to Vs, which is the final value. Again, Vc is constant, so the capacitance can be treated as an open circuit. However, between 0 and 5 tau, the capacitor voltage is changing. From t equal to 0 to t equal to 5 tau, the capacitor voltage changes from V0 to Vs. Now in this time zone, because the capacitor voltage is changing with time, the DC condition does not prevail. Because there is no DC condition, the capacitor may not be treated as an open circuit in this region. So it is important that we understand the three different time zones and the behavior of the capacitor in each of these three time zones. When the capacitor behaves as an open circuit and when the capacitor cannot be treated as an open circuit. You need to be clear about this point. Okay. So to determine the capacitor voltage after the switching, we need to know three parameters: V0, Vs, tau. How do we find each of these parameters? Finding V0 is similar to the case in source-free RC circuit. We consider the circuit for t less than 0, treat the capacitor as an open circuit and find the open circuit voltage, which is equal to V0, the initial value. To find the final value, we again treat the capacitor as an open circuit because now we are looking at a time which is greater than 5 tau. But this is t greater than 0. So to find Vs, we look at the circuit for t greater than 0. Treat the capacitor as an open circuit, find the open circuit voltage. This voltage is now the final value Vs. So for finding V0 and Vs, in both cases the capacitor is treated as open circuit, but V0 is obtained from the circuit for t greater than 0, whereas Vs is obtained from the circuit for t greater than 0. Finding R is the same as in source-free circuit. To find R, we consider the circuit after the switching, that is t greater than 0, and R is the Thevenin's equivalent resistance seen by the capacitance or between the nodes where the capacitor is connected. These 3 points can be summarized in these 3 bullets. To find initial value, we look at the circuit for t less than 0, C is an open circuit. To find the final value Vs, we look at the circuit for t greater than 0, again C behaves as an open circuit, and R is equal to RTh seen by the capacitance in the circuit for t greater than 0. To solve step response of RC circuits, we will need to apply all these 3 steps. Remember that the first step and the third step are the same for source-free RC circuits as well. Okay, this VC that we have obtained is called the complete response. The complete response can be separated into 2 terms as shown here. The complete response can be expressed as sum of the natural response and the forced response. Natural response is the response due to initially stored energy. Initially stored energy is considered in terms of the initial voltage V0, and forced response is that part of the solution which depends on the independent source in the circuit after switching, that is on Vs. So natural response is that part of the response which depends on V0, and forced response is that part of the response which depends on Vs. Mathematically, Vc is Vn plus Vf. Vn is the natural response, Vf is the forced response. The part depending on V0 is given by this expression, so this is the natural response. You can see that this is also the source-free response. So we can say that the natural response and the source-free response are actually the same thing. The both depends on the initial voltage or initially stored energy. The forced response contains Vs. There were two terms depending on Vs in complete response. We have collected those together. So make sure that we understand what natural response means and what forced response means. The complete response can be expressed as the sum of two terms in another way. In the other way, we can express complete response as sum of the transient response and steady state response. Transient response is the time dependent part in the response, and steady state response is the constant term in the response. So in this way, the complete response is the sum of the transient response and the steady state response. Transient response is the time dependent part. V0 minus Vs e to the power minus t by tau. This was in Vc. And the steady state response is the constant response. The constant response is simply Vs. So that is our solution. Okay, now let us solve a problem. In this circuit, the switch was at position B for a long time. At t equal to 0, it has been thrown to C. We want to determine VCT, we want to sketch VC, and we also want to find out the transient response, the natural response, and the forced response. First, we want to find V0. V0 is obtained from the circuit for t less than 0, treating C as an open circuit. For t less than 0, the switch is at B. So this is our circuit. This is the circuit for t less than 0. Here we consider the capacitor as an open circuit, and the voltage across the open circuit is the initial voltage V0. Using voltage divider rule, we find out that V0 is equal to 12 volts. Next, we will determine Vs. To determine Vs, we considered the circuit for t greater than 0 and again treat the capacitor as an open circuit. For t greater than 0, the switch is at C. So this is our circuit. If I show it properly here, this is the circuit that we get for t greater than 0. We treat the capacitor as an open circuit, and the voltage across the open circuit is Vs, which is our final voltage. Vs can also be found from voltage divider rule. If we apply the voltage divider rule here, Vs turns out to be 4 volts. Next, we determine tau. To find tau, we need R. R is the Thevenin's equivalent resistance in the circuit seen by C. In this circuit, between this node and this node, the equivalent resistance is RTh. Note that we have deactivated the 6 volt source because we are going to apply case 1 to find RTh. The capacitance is removed and R is obtained between these two nodes. 6 ohms and 3 ohms are in parallel, so R is equal to 2 ohms. So tau is RC, so that gives us tau is equal to 6 seconds. Now we know V0 equal to 12 volts, Vs equal to 4 volts, and tau is equal to 6 volts. We can find out the solution. Vs plus V0 minus Vs e to the power minus t by tau. Vs is 4 volts, V0 minus Vs is 8 volts, and tau is 6 seconds. So this is our complete solution. Now we want to sketch the solution. We have to first decide whether after the switching the capacitor discharges or charges. V0 is greater in our case, Vs is smaller. 12 volt versus 4 volt. So we can say that after the switching, the capacitor voltage will discharge, it will decrease. So this is the graph that we obtain. At t equal to 0, the voltage is 12 volts. At t equal to 5 tau is 30 seconds because our tau is 6 seconds. At t equal to 5 tau, the capacitance voltage reaches the final value, which is 4 volts. Okay, now we move on to the final part of our solution. We have to determine the natural response, the transient response, and the forced response. The transient response is V0 minus Vs e to the power minus t by tau. V0 minus Vs is 8 volt. So this expression represents the transient response. Remember, the natural response is V0 e to the power minus t by tau, where V0 is the initial value. Our initial value was 12 volt, so Vn, or the natural response, is 12 e to the power minus t by 6 volts. Finally, the forced response is that part of the solution which depends on Vs. Vs is 4 volts. So this is what we get for the steady state. I'm sorry, this should be the forced response. I should correct that. The forced response is the part depending on the final value 4 volts. That is all for today. Thank you.